Okay, so I'd like to start. Welcome back, everyone. So I think we're about ready to move on to a new topic, but I just want to finish off our discussion of the solid theory with some miscellaneous facts. So recall that we had this procedure that if we had a pair, say A plus, where this is some solid ring, and this is A plus a subring of power-bounded elements. Oh, sorry, just one. Then we associated to this, well, a certain solid analytic ring, which was specified by this mod A plus. And it was obtained by forcing all of the elements in A plus to become solidified variables. But recall that we also had the thing on the level of the derived category, and this is.
So what happens if if A plus is not a subring of A0?
Then when you enforce this condition, you might lose the A might no longer live in that category. So you'd have to apply the localization and get a new A, a sort of the completion in some sense. Okay. Yeah. But we also had this. And recall that this was defined by it was defined as a full subcategory of here consisting of those objects whose homology lies in here for all I, and we showed that you have a nice left adjoint with the exact same properties as the left adjoint here, symmetric monoidal, and so on and so forth. But there was this subtlety that this is not necessarily, in the full generality of an analytic ring, this is not necessarily equal to the derived category of this. And the basic reason is that if you take some basic object here and apply derived solidification, it might not live in degree 0. That's kind of the obstruction. So in fact, the generator here, so there's a compact projective generator, which is equal to, you take the compact projective generator we know and love from the solid Z theory, and then you simply tensor it in the sense of the solid Z theory with this solid ring A. And that, we know that it doesn't matter whether you take the derived tensor product or the ordinary tensor product there, because as Peter showed in one of his lectures, this is flat in solid Z. So that's what means that if you did the derived analog of this definition, it would literally just be the derived category of this abelian category. But then what's the generator here? Compact generator of this derived category. Of this thing. So what do? You take this object here and you localize it with respect to this derived localization functor. So you derived A plus solidify. And maybe I'll say, so theorem. So first thing I'm going to explain is that this lives in degree 0. And that means it's a compact projective generator for the abelian category, mod A plus solid, and the derived category of this abelian category is the derived category that we defined there. So as long as your underlying solid ring is not derived in any way, then in fact the whole theory is, or that doesn't have any, the whole theory is kind of flat, so to speak, determined on the abelian level.
Does it, so is it a change from what was said before, or because I remember that it was not clear in the previous talk, I mean, no, it was not clear that this was...
Well, that's why I'm explaining it now, yeah. Okay, so how do you access this derived asolidification? So being A plus solid means that you're solid for any variable mapping in. So what I want to claim is that claim is that this derived A plus solidification you can actually write this as a filtered colimit. So it's all happening element-wise in A plus. And you can write A plus as a union of rings which are finitely generated over the integers. So let's say R subset A plus are finite type over Z. And then,
So you just forget to write the square in a more A plus in there? Or?
Oh, yes, thank you. Yes, I did. Yeah. Yeah.
Oh, well, is it asking the difference between when there is a square and not?
Yes, sorry. That's, yeah. So you could take M, which is a priori an A module, but you can, A plus maps to A, and therefore R maps to A. You can treat it just as an R module, and then you can do the derived R solidification. So this is a filtered colimit. So the point is, well, there's two things to check. First of all, you need to check that, well, there's a map. You need to check that this is derived A plus solid. And you also need to check that in this functor, if you have something which is, yeah. And then you need to check that if you map out to anything derived A plus solid, then it doesn't see the difference between this expression and this expression. So why is it derived A plus solid? Because derived A plus solid is the same thing as derived R solid for all R subset A plus finite type, just because it's simply an element-wise condition on the algebra. So certainly the R term in this thing is derived R solid, but also any further term in the filtered colimit after the R term is also going to be derived R solid, because it has an even stronger property of being derived like R prime solid, where R prime is bigger than R. So there's a cofinal system of things in this filtered colimit which are derived R solid for any fixed R, and we know that a filtered colimit of R solid things is R solid. So it's going to be R solid for all R, and therefore it's going to be A plus solid. And then mapping, if you map out to something A plus solid, then in particular it's R solid for every R, and by a similar argument you see that there's no difference on maps from M to this or this filtered colimit to this. Okay? So it suffices to analyze to show that if you take this product Z, tensor Z solid A, and then you derived R solid, R solidify, this lives in degree 0. But this, we can do it in 2 steps. So we can see this as you take your first base change to the solid R theory. So you take this thing, and then you derived R solidify. And then you derive tensor in the solid R theory with A. So it suffices to see that well, first of all, that product Z tensor Z solid R derived solidify well, this lives in degree 0 and is flat with respect to our solid tensor product. Okay? So by the way, let me note, before I continue with so basically we have to analyze R solid when R is finite type over the integers and prove analogs of what Peter already explained for Z solid. So we have to calculate this basic generating object, make sure it lives in degree 0, and we also have to check that it's flat. But before I go on and do that, let me note a corollary, which is kind of a corollary of this filtered colimit type of argument. So so we have a compact projective generator of this abelian category, and I basically just analyzed for you that it's gotten by some filtered colimit of the thing you see over a finite type ring. So let me say that, so if R is arbitrary, commutative ring, then, well, one thing you can say is that solid R, by which I mean solid R, comma R, so you solidify all of the elements in R. This is equal to in of the finitely presented elements in solid R. And the finitely presented things are the things which are just co-kernels of maps between finite direct sums. Well, you don't need that, but of this single compact projective generator that you have here. And so also, if you want to know about this finitely presented category, it formally reduces to the finite type case. So in some sense, all of the completion is happening at the level of finite type subrings. And then the rest is just some algebraic filtered colimit. All right. So now we need to do this analysis here. So I'll make a claim, which is basically that it works just like in the case of solid Z. So if you take product Z, tensor solid Z R, and then you derive solidify, then this is just the same thing as a product of copies of R. And if I forget to say an index set, it's always going to be countable. Okay.
You mentioned this is finite type case. Huh?
Sorry? Finite, yes, thank you. Yeah, R finite type over Z. Thank you very much. So by this discussion, if R is not a finite type, what you would instead be seeing is So if R not finite type, then it's equal to the union over all finite type subrings of the product of copies of R prime, which is smaller than the product of copies of R. Okay, so proof. So first consider the polynomial ring on finitely many variables. Then we've essentially already seen this. So we saw that the derived T solidification of a free module commutes with all limits and colimits and sends Z to just to Z bracket T. So well. So if you do X1 solidification, then that just gives you product X2, Xn. And then you just keep going. You do X2 solidification, X3 solidification, and so on. And it always just throws the variables inside the product instead. And in the end, you do end up with product of Z X1 up to Xn. So here we recall that if you do ZT solidification of a module tensor over Z with Z bracket T, this commutes with limits in M, and it sends Z to Z bracket T. And we're also using that the different solidifications commute. So that you can actually do the solidification with respect to all of them by just doing them one by one. And when you do the X1 solidification and you X2 solidify it, it'll still remain X1 solid.
You also use that if it's X and Y solid, then it is solid for everything.
Yes, in the subring generated. Yeah, exactly. So that so that to solidify for R, it's enough to solidify for all the variables in R. Yeah.
So you don't use it, you put it.
Well, right, but we're using it. Oh, well, this is, yeah, this, I guess it also follows. Yeah, that's true. The argument for that was basically this anyway, but okay. It's probably good to mention it in any case. Okay. Now, in the general case, so let's say we have a quotient, so x1, xn is projecting onto R. Then, product Z, tensor Z solid, R, derived R solidify. You can get it in two steps. Again, you can Z solid and then you've already solidified with respect to a generating set for R, so you're actually already R solid, and the only thing you need to do is do an algebraic base change from this ring to the ring R. So derived, everything should be derived. But we already figured out what this is, that this was the product of ZT1 up to Tn, and then we so we're left with just analyzing this and proving that it's equal to a product of copies of R. But so ZT1 up to Tn is Noetherian. That means R can be resolved by potentially infinite resolution, but a resolution by finite free modules And for each of those finite free modules, it's clear you just bring it into the product. And then it follows that the same holds for R on the level of this derived tensor product. So then, so you can look at the class of z x1 up to xn modules for which this claim is true with R being replaced by that module. And that class contains the ring, of course, and therefore it contains anything that can be resolved by direct sums of copies of the ring as a
Also, the product, the infinite product of copies of ZT1 Tn is, I think, flat over ZT1 Tn. Again, it's a property of Noetherian or coherent ring.
Yeah, yeah.
At least in the the usual product, but here it's condensed mass product. But still, I think for every condensed set, it's the value of this on it probably is.
Yeah, that's another argument. That's another possible argument. But I mean, for me, this is a little more straightforward. Yeah.
Yeah, because the flat, I believe, I don't remember, the flat thing just uses coherence. Okay. So the product of flat is coherent ring, but now you use the fact that the ideal is a finite type to actually see that when you quotient out, you get a product of copies of R. Otherwise, you would get a limit of product of colimit of product of finite quotient of finite type ideals.
Yeah.
So and again, it is condensed set by condensed set. It's the same. It's verified by elementary way.
Yeah. I mean, for me, this is pretty elementary, but okay. I don't know.
No, because in theory, to compute this tensor, you have to resolve on the left. I mean, tensor has different meaning. I mean, when you base change from the category of a ring to another ring, you are supposed to resolve the original. No, okay. You can also compute it by resolving the other.
I don't need to. I mean, I really, this argument just works in the derived category. I don't need to worry about resolving this. It just. I mean, the argument is. I claim there are no gaps in this argument.
No, because when you resolve a ZT1 Tn, you are leaving the derived categories of R, and you have a derived category of some other.
No.
But the map is defined already, so to check it as isomorphism, you can pass to the derived category ZT1.
No, I have a resolution in this algebraic category, and then I have this tensor functor taking me to this derived category, and that tensor functor preserves colimits, and I get a resolution there. It's really fine. Okay. So, yeah, this is quite technical, I'm afraid, so we've proved now this claim that this derived R solidification lives in degree 0, and that was the first thing we needed to show. But the second thing we needed to show is that it's flat with respect to the tensor product. So for this, we're going to analyze this category of solid R modules in a little more detail. So this structure of solid R. So again, let me say maybe theorem. So again, R finite type over Z. Then, well, something we already know from this being a compact projective generator is again that solid R is just the in category of its compact objects, which are the finitely presented ones. So these are the things that are co-kernels of maps between the compact projective generators. But the second claim is, so you could say coherence. This category, this subcategory, is an abelian category. It's closed under kernels, co-kernels, and extensions.
This is same as this corollary.
Which corollary? Yeah, the first part is obvious, or sorry, well, the first part follows from the fact that we have a compact projective generator of this category. Then the compact objects will all be built from finite colimits from that, and they will be generators, and it follows formally that it's the ind category of that. So what we really need to check is that we have this, that this is an abelian subcategory. Now, let me remind you a bit about some classical commutative algebra. So a classical commutative ring is called coherent if you have the analogous property in the setting of discrete modules. So that the finitely presented R modules form an abelian subcategory. But you can check by playing around with short exact sequences that you only need to, there's only really one thing to check, which is that every finitely generated ideal is actually finitely presented. And those same arguments in this setting show that it suffices to check so every finitely generated subobject of product of copies of R is finitely presented. So CF coherent rings. Now I'm going to use a bit this notion quasi-separated. So note that if you have any subobject of product of copies of R, well, this is quasi-separated, i.e. Hausdorff. And any subobject of anything quasi-separated is also quasi-separated. So this is also quasi-separated. So it suffices to show, for this, it suffices to show that every finitely generated quasi-separated solid R module is actually finitely presented. So let me make a lemma. So if M in solid R is quasi-separated, then the following are equivalent. One is that M is finitely presented. Two is that M is finitely generated. And three is that, well, you can say exactly what M looks like. So M is an inverse limit of MNs, where each Mn is a finitely generated R module, discrete R module, and the transition maps are surjective. And the category of these is just the countable pro-category of the category of finitely generated R modules. So the maps between such inverse limits are just the maps of pro-objects.
Pro-objects with surjective transition maps.
Yes, thank you, thank you. Yes, yes, yes. Yeah. Yeah. Okay. So So the non-trivial implications are 2 implies 3 and 3 implies 1. So for 2 implies 3, well, we finitely generated by definition means we have some surjection from product of copies of R, and then there's some kernel. But since M is quasi-separated, it follows that this inclusion is a quasi-compact map of condensed sets, which means, so this object is quasi-separated, so it's just some filtered union of compact Hausdorff spaces. And this means that when you restrict this inclusion to any of those compact Hausdorff spaces, you get a closed subset. But this is one of those sequential spaces, metrizable spaces, in fact. And so being a closed subset on any compact subset is the same thing as just being a closed subset. So this is the same thing as just a closed subset in the topological sense with the product topology.
Closed subset, which is also in our module, and this is the same. The associated condensed module is the one that we are talking about.
Right. But now we can look at, for any n, we can look at the projection. So we have K subset product R. We can look at the projection onto like the first n coordinates. And then if we can let Kn be the image in here. Then it follows that K is just the inverse limit of Kn's. And these have surjective transition maps, i.e., so K is as in 3.
No, you know that M is as in 3, but this also follows.
Right. I wanted to know that M is as in 3, but this also follows. Yes. And that, yeah, then, yeah, and M will analogously be inverse limit over n of Mn, where Mn is a product. Okay. And note that this argument shows that so in particular, if you start with an object as in 3, yeah, okay. So now we also see to finish, i.e., to show that 3 implies 1, it actually suffices to show 3 implies 2. Because if we know that this guy is finitely generated, then it fits into something like this, and we just prove that the kernel is of the same form, and then it will follow that it's finitely presented. But then this is actually elementary, so you have like M1 surjecting onto M2, surjecting onto M3. You can make some finite free module surjecting onto M1, and then you have some kernel here, kernel of this map here, and then you can make some R direct some D2 surjecting onto that, and then you can make a system R direct some D1, R direct some D1 plus D2, and in the inverse limit, you get a product of copies of R surjecting onto M. So in fact, if you're wondering about surjection on the level of condensed objects, in fact, you can even get a topological splitting for the map of topological spaces. So by kind of section here, make a compatible section there, and so on. If you're not worried about R linearity, which you're not, then you can get this quite easily. Okay. So that's the proof of the lemma. So the quasi-separated objects are just these kind of classical R modules. And that also proves the the coherence here.
And extensions is easy.
Extensions is formal, yeah.
Yeah, it doesn't require anything. Because it's projective generator, so it's...
Yeah, you can lift. Exactly. I mean, actually, because you have this compact projective generator, you're equivalent to the category of modules over a ring. And so it's really, you can actually just quote the usual theorem from commutative algebra. Okay. Yes?
Sorry, so here, so if M was finally generated, in particular the kernel also had this really nice property of having property 3 as well.
If M was quasi-separated and finitely generated, yeah.
And so that in particular implies that if M is finally generated, you can find the resolution of M by like really nice size, like finally.
Yeah, that's right. That's right.
You said something about commutative algebra, but in fact the endomorphisms of the projective object is an associative ring.
Yes. Oh, yeah. Sorry. Yeah, not commutative algebra. Sorry. Thank you. Thank you. It's not commutative algebra. It's module theory over a non-commutative ring. Yeah. Thank you. Yeah. Yes.
Wait, we're still proving the theorem?
We're done with that theorem.
Where did we use the fact that it was finite type over Z? Sorry.
Well, it was used in order to say that this was the compact projective generator. So so a priori you take product Z tensor up to R and then solidify with respect to R, and only in the finite type over Z case when you had this rejection from the polynomial ring. Yeah.
But for any Noetherian ring, you can take the product of copies of R.
Yeah, if you just say that you build a category that has this as compact projective generator with the endomorphisms, what they have to be, then the rest of the arguments here work for an arbitrary Noetherian ring. Yeah. Okay. Right, and we're not quite done with the first theorem because we still need to show that product of copies of R is flat. So now we make a claim that if M is finitely presented in solid R, then if you take M derived tensor product R solid with product of copies of R, you just get a product of copies of M. And in particular, this lives in degree 0. No. And that implies that this theorem, or this claim implies that this guy is flat. Because the derived tensor product with any finitely presented object lives in degree 0, but every object is a filtered colimit of finitely presented objects. So the derived tensor product with any object will live in degree 0, which is the same thing as saying you have flatness.
So incidentally, to define the derived tensor product, maybe we didn't spend time on this, but in the usual approach, you need to know that there are enough flat objects relative to tensor to define classically the derived tensor product.
Right.
So here, what is the approach? What's the meaning assigned to the derived tensor product? Do you prove that there are enough flat?
It's not really necessary. So first, on the level of the derived category of light condensed abelian groups, I mean, you can take this perspective of sheaves with values or hypersheaves with values in the derived infinity category, and then you can just sheafify the section-wise derived tensor product of abelian group, derived sheafify the section-wise tensor product of derived abelian groups, and that's a fine definition of the derived tensor product on that basic thing, and then it just gets ported to all of the other contexts. You know, you have a ring object in there, you have, then you just do a relative tensor product, and then you have some localization, but we already argued how to get the symmetric monoidal structure on the localization given by an analytic ring structure, and so on and so forth. So it's not actually, to make the definition, it's not actually necessary to know anything about flat objects.
So for condensed abelian, okay, so let us say without solid, you just have a flat, the tensor for, okay, there we know initially that there are enough flats.
Indeed, in fact, in light condensed abelian groups, we do know there are enough flat objects. So that's, I didn't need that infinity stuff really to, you're right, yeah. But I mean, yeah, I have to say, I was kind of off the top of my head just saying how I think about it. But yeah, these free object on a light condensed set will itself be flat, and yeah, okay. Okay, so where was I? So we have to finish the discussion of, so far we just need to prove this claim. So proof. So we are finitely presented, so we can make a surjection here where the kernel is finitely generated. But the kernel is also quasi-separated. So, you know, it'll also be finitely presented. Well, we can basically just continue to make an infinite resolution. So, and that reduces us to the case where M itself is equal to this product of copies of R. And then we can remember that this was product of copies of Z, tensor R, and then R solidified. And then that will reduce us to the analogous fact for products of copies of Z, that it distributes over infinite products.
So for infinite product of Z, for Z, then you reduce to light condensed abelian groups, this infinite product of Z, and there.
Yeah, there are even the thing. So then you have this nice object that solidifies to a product of copies of Z, this thing we were calling P, basically n union infinity. And that light condensed set has the property that if you take its product with itself, it's isomorphic to itself in the expected way. Or like that object for n times itself is the same as that object for n cross n. And yeah, you just, well, anyway, it was explained. Okay. Any other questions?
Of course, this is projective. This is the product of copies of R, the projective generate. Okay, but if you did not define a tensor L as a classical left-derived factor, you cannot use the fact that the higher vanishes for projective object. I mean, this requires a classical treatment.
Yes.
But
right.
But
so explain also that the derived tensor product is actually the derived factor of the tensor product.
Right. That I could have added to the. I could have added that to, yeah, that's right. That's another important claim. In addition to the fact that the derived category of this abelian category is the derived category that we defined, you also have that the derived solidification is the left-derived functor of solidification. You have that the derived tensor product is the left-derived functor of the tensor product, and you can resolve in either variable. This all follows once you know all of this flatness and living in degree zero stuff.
so again, so the foundational way you define tensor L for your derived category of solid is what, I mean, without using flat objects.
Yeah.
So the way you do it is that, of course, it lives in some derived category without solid.
Yes.
So you can just take tensor there and solidify.
Yes, exactly.
Of course, you have to know that somehow, then part of this story is that solidification commutes with, I mean, if two things have the same solidification after derived tensor, I mean, you have to know, but then to define a derived without solidification, then it is just derived over, this is just modules over a ring. Suppose you already know over Z how to define it.
Yeah.
Then over a ring, you use flat object, or what do you use?
You never have to use flat objects to make the definitions.
Okay, so how do you define the derived tensor product for without the solid?
Yeah. You have a commutative ring in solid Z, and you want to do a derived tensor product. I mean, explicitly, it's it's some geometric realization of a bar construction where all the tensor products over solid Z are derived. I mean, so Lurie sets it up. If you have a commutative algebra object in a symmetric monoidal infinity category, then you get a tensor structure on R modules in there.
Okay, so you can have in this general setup, you have some way to...
Yeah, I mean, it's basically like you take M tensor Ln, M tensor Lr, tensor Ln, M tensor Lr, tensor squared.
Okay.
And then you have some simplicial object, and you take the co-limit, all in this infinity sense.
Okay, so you have this general way of viewing the tensor product, and then it always, in all cases, there are enough flat objects, and you can use flat or okay.
In what we've discussed so far, the solid theory, yes, that's what we've just proved. Although, as you see, it's not a formal argument by any means. You really have to analyze what's going on. Other questions? Okay. Oops. So I want to spend just a little more time on the homological algebra of solid R. Because Peter also explained something else in the case of solid Z. Basically, that every finitely presented module, it doesn't just have an infinite resolution by products of copies of Z, but it actually has a two-term resolution by products of copies of Z. So that kind of, at least from the perspective of finitely presented objects, you have sort of homological dimension 1 for solid Z, just like you have for usual Z. So I want to present a generalization of that. Theorem. So if R is finite type over Z and is regular, a regular ring of dimension D, then if you have M in solid R finitely presented, and you have N in solid R arbitrary, say, then X, even internal X, why not? The X's vanish in degrees bigger than the dimension.
And the Tor vanish also in degree.
Right. So a corollary of this will be that if you have a finitely presented module, then you actually get a projective resolution of length in most, well, depending on how you define length, D or D plus 1. Yeah, maybe, yeah. And then we already saw that the projective objects are flat, so this also implies a bound on the tors. So a corollary is, so if M is, and that passes from finitely presented to arbitrary. Let me say HI. Okay? Let me caution this statement does not extend to non-finitely presented M. So unlike in the case of discrete modules over a Noetherian ring, regular Noetherian ring of finite dimension, there you actually have the X vanishing for all modules. There's some extra argument for going from the finitely presented case to the general case. That argument does not work in this context. And in fact, I think you can have arbitrarily high X even for solid Z. So let me give here's a fun exercise you can try to do. So you take two distinct prime numbers. This is just cute. So here's something that's not finitely presented, because you're quotienting by something which is Z1 over L. Then if you do there's an X2 which is non-zero, and it's given by switching the roles of P and L. So that's just if you want to have a little fun with some calculations.
And the n of X2, and you claim also there are n arbitrary high X?
I believe that, so certainly, there exists a model of ZFC in which there are arbitrarily high X. So there's logicians analyzed a particular X group, which I think Peter also mentioned in one of his lectures. But I think even in ZFC, it should be possible to produce arbitrarily high non-vanishing X. I mean, even in any model of ZFC. I mean, you run into, a priori, if you want to go from the finitely presented case to the general case, you have to analyze derived inverse limits along some arbitrary filtered system.
But do you have the bound on the cardinality? Because if you are in a model where the continuum hypothesis holds,
yeah,
and if you look at, or maybe generalize, I don't know, if you look at all possible finite types of modules,
yeah.
So they are maps, it's related to maps from product of Z to product of Z.
Yeah.
Then the cardinality of this space is like Aleph or to the Aleph.
Yeah.
Anyway, it is one of those things. It is some finite Aleph n. If it is some finite Aleph n, then we have cohomological dimension results for this.
Yes.
So it suggests that there would be a bound for for quotients of a thing of a projected general by something, but then there is a classical argument in ring theory which probably extends to this case that if you know the X vanishing for this kind of ring modular arbitrary ideas, then you have it for arbitrary.
Yeah, but so you need to, but the analog of that argument shows you need to analyze something like an arbitrary submodule of product of copies of Z, not necessarily finitely generated, and then but I guess there's a bound on the cardinality there. Yeah, so you're right that the cardinality of
The possibility that they are finite.
What's that, Peter?
It could be that this argument actually proves that there's something that's continuum possibility to have finite homological dimension.
Maybe, yeah, it's possible. Yeah. But if the cardinality of the continuum is larger than Aleph n for any n, then you should probably get arbitrary higher X. Anyway, let's not go there. Right. Where are we? So let's try to prove this. So. So the first claim, first case, we're going to take n, so by the same argument, sorry, just a sec, maybe I'll do that at the end. So the first case, let's say that n is actually classically finitely generated module over the Noetherian ring R. And then let's take M to be quasi-separated, finitely presented solid R. So then that's an inverse limit of MNs over all n with surjective transition maps. And in this case, the claim is that x I from m to n, or I guess it doesn't even need to be finitely generated. Let's just say discrete is the same thing as the filtered colimit of xi over r. So this is r solid, xi over r from mn to n.
Didn't you prove that finitely presented implies quasi-separation?
No. No, certainly not. I mean, in the solid Z case, something like p-adic integers mod integers will be finitely presented, but not quasi-separated.
So what did we prove?
Proved that if you're quasi-separated and finitely generated, then you're finitely presented.
And if you're finitely presented, are you? You're not necessarily quasi-separate?
Exactly. Exactly, yeah. So for example, ZP modulo Z is finitely presented.
So a map from product of copies of R to product of copies of R is the cokernel is not quasi-separate.
Not necessarily, that's right.
Okay, I misunderstood this point.
Yeah, that's important. Yeah. So we need to show that, so we need that the RHOM, you can pull out the inverse limit. Basically. By the way, the claim for internal follows from the claim with underlying. It's just replacing n by like continuous functions with values in n for some profinite set S. But so we have the Mittag-Leffler, so we have the resolution. Some kind of usual identity minus shift sort of thing, or maybe it's or shift times f, or some kind of shift map. So this distinguished triangle here, so that tells you that the question of pulling RHOM, the inverse limit out of the RHOM, is the same as the question of pulling out a product and turning it into a direct sum. And then we can resolve product mn by product r to reduce to RHOM product r n equals direct sum RHOM r n, which follows from this being projective and the basic calculation on HOM. Okay. So from this, it follows that we get the desired bound on X if n is a classical discrete R module and M is finitely presented and quasi-separated. Now, you can always result, so now M arbitrary finitely presented, not necessarily quasi-separated. Then you can always resolve, M by a product of copies of R, and then the kernel will be both finitely presented and quasi-separated. And then analyzing the long exact sequence in X, mapping out to N, you would get the desired result, but with, you'd lose 1 degree of cohomological dimension. You'd get that xi vanishes for I greater than d plus 1. So the xi vanishing here for I greater than d when you chase through the long exact sequence would only give the vanishing in degrees greater than d plus 1 there. So this naive argument only gives x I m n equals 0 for I greater than d plus 1. So we have to do a little bit of extra work to improve this.
Wait, for that conclusion there, we didn't use regularity? Or?
Well, we did, because I should maybe recall the classical fact. So recall, so if R is regular Noetherian dimension D, then the classical X groups between discrete modules. So the question now for quasi-separated things in the solid context reduces to the classical question in discrete commutative algebra. And that's where we use regularity. Yeah. So we're going to do a less naive argument. So we're going to continue the resolution 1 more step. So instead, so we have a product of copies of R. We can surject again from a product of copies of R. And now at this point, we take a kernel. And we get a resolution like this. This is still quasi-separated. And then it suffices to show, to prove x I m, different n, I'm so sorry. So let me say x. For I greater than d, it suffices to show for I greater than d minus 2. So we bought ourselves 1 extra drop because we continued the resolution 1 step more.
Maybe you should say that equal to 0 and 1 have to be handled by.
That's true, yeah. So I'll be assuming, assuming d greater than or equal to 2, the case d equals 1, well, you can use similar arguments in low dimension. Yeah, thanks, Peter.
So on d equals 1 is the same as for integers?
I'm not entirely sure, but a modification of this argument for d greater than or equal to 2 will also work for d equals 1. Right. So it suffices to prove this x vanishing. So now we want to find a nice expression of n as an inverse limit of finitely generated R modules. So there's actually two ways of writing n as an inverse limit of finitely generated R modules. So the first way is just the argument we already had, where this is the kernel of a map between quasi-separated things. So it's a closed submodule here. So we can always just look at the, well, maybe I'll make that the second method. Sorry. The first method would be we analyze this map here. This is a map from product of copies of R to product of copies of R. Again, that's the same thing as a map on the pro system. So if you restrict to any initial chunk of this, then there's some corresponding initial chunk here where the map projecting onto that factors through projecting onto this chunk, and then just a map of discrete modules there. So if you re-index and allow like finite free modules here instead, so then you can assume that this map here comes from an inverse limit of compatible maps from the initial chunk, the nth initial chunk here to the nth initial chunk here, just by re-indexing. And then if you take the kernels of those maps, so you take well, let me say, I don't really need it to be a product anymore. So we take an inverse limit of this type, and we say that this is given term-wise. So then we can take, so we can let, so then we have n equals inverse limit over n and n. But the other thing we can do is we can let n prime n, which will be contained in nn, contained in fn, be the image of n mapping to inverse limit of fn mapping to fn, or the particular fn, inverse limit fm mapping to the particular fn. So number one has so each of these presentations of n has something good and something bad about it. So good news for one is that you have this xd minus 2 vanishing, xi nn x equals 0 for all I bigger than exactly what you want, d minus 2. But the bad news, no guarantee that this system nn is Mittag-Leffler. Which is needed for x to I nx equals filtered colimit over n of x to I and nx. So that's unfortunate. So in the argument I presented here in the case where the transition, I said the transition maps were surjective, but the argument really only used that it was a Mittag-Leffler system to get this resolution here. And then in 2', in 2, the situation is opposite. Mittag-Leffler, in fact, the transition maps are surjective by construction, but no guarantee that x d minus 1 n prime nx equals 0.
So n prime n is this condensed module, or
No, it's just discrete. So any sub-object of a discrete object is itself discrete.
all right. So we know that this is but we know that n is the limit of both in the condensed sense.
It's the limit in the condensed sense of both of these systems, yes.
Okay, but certainly you can produce an example of map from lim fn to lim fn prime, for which the kernels would not be Mittag-Leffler.
Yes, exactly. Yes, you can. Yeah.
Occurs in nature.
Yeah. Yes. Right. So what we have to do is find something in between that has the good properties of both. So I apologize, this argument is a bit technical. By the way, the reason we have this nice property here is that it's a kernel of a map between projective objects So it's like so if you took the co-kernel, then it would be 2 steps away from that co-kernel. So the vanishing in degrees greater than d for the co-kernel will imply the vanishing in degrees greater than d minus 2 for that long kernel over there. That's why you have this. And but for this nn prime, you don't know that it's a kernel of a map between projective things. You only know that it's sitting inside a projective thing. So you'd get vanishing of xd, one better than for a general module, but you wouldn't get vanishing a priori in degree d minus 1. So that's what we need to fix. So what is the difference? So we're going to find n double prime n sitting in between them, and such that we get x vanishing and n double prime n is Mittag-Leffler. So if we get this, then we're done, because the inverse limit, we would get the desired x bounds for the inverse limit of the nn primes, but that's sandwiched in between these two things which have the same inverse limit, which is the thing we're interested in. So the vanishing of x for this inverse limit would imply it for our desired vanishing for n. Okay? So now we use a bit of commutative algebra. So what is the obstruction? We have a module where we know the vanishing in degree d, but we don't know the vanishing in degree d minus 1. The obstruction having this is that. So the obstruction is in some sense concentrated at the closed points. So it's a question of depth. So the Auslander-Buchsbaum formula tells you that for a regular Noetherian local ring, the projective dimension of a module plus the depth of the module is equal to the dimension of the ring. And because we have the one better estimate on the projective dimension, the only rings that are going to give us obstruction are the local rings at prime ideals, which are actually maximal ideals, so that the local ring has maximal dimension. And the only obstruction is going to be moving from situation of depth 1 at that maximal point to depth 2. So is the fact that at a maximal ideal, so n and prime n only known to have depth 1. Yeah. Yeah.
Apparently many closed points. And you know that it lies inside the other one because the other one is, as this,
yes,
is reflexive.
Yes.
And so, and then you have to establish Mittag-Leffler, but you only different finding many closed points. The classical length argument works.
That's correct, Ofer, yes. Okay. All right. Maybe I'll just repeat what Ofer said. So what you can do is if you, let's say for simplicity you only have a problem at one maximal ideal. In general, you'd fix a problem at finitely many, and then if you increase the number of them, eventually the situation would stabilize by Noetherianness. So let's say there's a problem only at one maximal ideal. Then you can look at the inclusion of spec R minus that closed point x, closed point, into spec R, and then you replace n prime n by j lower star j upper star of n prime n. And that receives a map from n prime n, but it's in fact an inclusion due to the depth 1 assumption on our module. But then on the other hand, by this procedure of this extension and restriction, so depth is, you can characterize depth in terms of local cohomology at the maximal ideal. And that's exactly what comes up when analyzing the difference between this and, say, the derived version of this. And using that, you can see that this improves the depth. So this is depth 2 at x. On the other hand, if you were to perform the same construction for nn, since we already know this has depth 2, you wouldn't have been changing it. So you really are producing something sitting in between, which fixes the problem at a given closed point. Then there's the Noetherianness, which tells you, well, it's only finitely many closed points that are going to be involved. So you can, by the same procedure, you can fix the problem, all the problems for n prime n, and in a compatible manner in the tower. OK, so that's, then you've got it to be depth 2 at all the closed points, which gives you the desired ext vanishing for these n double prime n's. And then what about the Mittag-Leffler? So Mittag-Leffler. So this tower n double prime n sits in a short exact sequence with n prime n and the quotient n double prime n mod n prime n. So to show that this is Mittag-Leffler, you need to know that this is Mittag-Leffler, or it suffices to show that this is Mittag-Leffler and that is Mittag-Leffler. This one we know because the transition maps are surjective, but this one here is supported at, but it's supported at finitely many closed points. And it's a finitely generated module over the ring, and that implies that it's finite as an abelian group. Because remember, our ring was finite type over Z, the maximal ideal is all, of course, have, the residue field is a finite field. And a compactness argument shows that any inverse system of finite abelian groups satisfies the Mittag-Leffler property. So compactness gives Mittag-Leffler. Okay? It's a bit of a, yeah. Okay, so that gives the ext vanishing, to sum up, summary of what we've done so far, we've seen that if M is finitely presented, solid R, and if X, I've switched to X, is a discrete module, over the ring, then we get the desired ext vanishing. Now suppose X, if X is quasi-separated and finitely presented in solid R, you write X as an inverse limit of Xn with surjective transition maps. And then the R homs into that will just be the inverse limit of the derived inverse limit of the R homs into each of those terms. Now, in principle, you might get one worse again because there could be a lim 1 in the last inverse system. But because that last, that's talking about the xd's into this. But since these transition maps are surjective and d is the largest degree at which you have non-zero ext vanishing, you actually see that on xd's you get surjective maps so that there's no lim 1 potentially giving you something in degree d plus 1. So you get the claim for D. And then X arbitrary finitely presented. Then you resolve it by, and the X with values in X can only be better than the X with values in these two. So you get that situation as well. And then finally, for an arbitrary, so x arbitrary. So if you write x as a filtered colimit of xi's, where these are finitely presented, then x I from any finitely presented m to x is the filtered colimit of x I. Oh no, I shouldn't use I, xj m to xi by pseudo-coherence of m. So you can resolve m by products of copies of R, and then this follows from products of copies of R being compact projective.
What about the x underline?
It's this, so yeah, I should, from this point on, so this claim for an arbitrary discrete module implies the same claim for underline because it's the same as s-valued points of this thing is the same thing as xi from m to continuous functions from s to this discrete thing, which is just another example of a discrete thing. So then you get this there, and then from that point on, all of the arguments actually work at the internal x level.
Including the lim1 argument.
Including the lim1 argument, yes.
Because you reduce it to an x.
You reduce it to showing that a lim1 vanishes in condensed abelian groups, and the terms in the system are discrete, and the system is Mittag-Leffler, and that those properties are preserved by, and if you take continuous functions with values in that, it's still a system of discrete things, and the transition maps are still Mittag-Leffler, or surjective even.
Yeah, and in the condensed abelian group, again, you have only up to lim1.
Yes.
You don't have more because you can compute it term-wise.
Yes. Because products are, because countable products are exact. That's the reason.
Okay, we prove the countable. Okay. And you can compute the lim1 term by, no, maybe this is not, you can compute lim1 on each object, not necessarily project. Okay, you don't have projective, but still you can compute the lim1. It's not like in any site where it's delicate, you cannot compute. But here you can compute the lim1 on any test condensed set. No, for some things.
Yeah, so certainly for this P object, you can because that's projective. And then that's enough for solid because we know that the solidification of P generates. So that's one argument you could give. I'm sure there are other arguments as well, but yeah. I mean, but you know, the lim1 is always just going to be the sheafification of the, you know, the condensed lim1 will always be the sheafification of the naive section-wise lim1. And so if you prove the vanishing of the lim1 section-wise, that's enough to prove. Yes?
I missed where pseudo-coherence comes from.
Right. So that comes from the claim that the finitely presented objects form an abelian category, which has as a corollary that for any finitely presented objects, you can build an infinite resolution where all of the terms are products of copies of R. You're welcome.
And to have non-quasi-separated finitely presented object, the ring has to be of dimension at least 2, or?
Non-quasi-separated finitely presented has to have dimension at least 1.
At least 1.
Yeah. So if you're over a finite field, then every finitely presented object is quasi-separated. But once you move to, say, the integers, then as I said, ZP mod Z is an example of something that's not quasi-separated, but is finitely presented.
Also, in summary, the step of reducing to reduce from quasi-separated finite presented to to discrete one. Is that easy to see? There is no lim1 here. Like
Which step? Sorry, this step here. Yes. Yeah, you see that there's no lim1 because the only lim1 that can contribute to degree d+1 is the lim1 of xd's. And because on the level of these guys, we know that there's no x for any discrete module in degree d+1, you see that if you have a surjective map, then xd's into it will also be surjective. because the obstruction is an xd plus 1 of the kernel, which vanishes. Well, so then the xd's is also a Mittag-Leffler system. So, yeah. Okay, that was that took longer than I anticipated. I had a couple of other topics I wanted to discuss, but at this point I probably have to choose. So maybe I will, maybe I just want to make a point and illustrate it. So recall, so if R is now a discrete commutative ring, so we showed that that solid or D, let's say RZ solid localizes over this valuative spectrum of the ring. This localization had the property, and this is maybe why it's convenient to analyze. One reason why it's convenient to analyze that if you on this discrete level, if you take the unit object here, which is R, and then you restrict to any of these basic quasi-compact opens, then you still just get another discrete ring. In fact, if it was the rational open like given by F1 up to Fn over G, then the ring was just R1 over G. So with this localization, you're kind of staying in the world of your ambient ring being discrete. But this is by no means, there are also other ways to localize the same category. This is by no means the most general possible localization. It's the one we discussed because it's the one that's most closely related to Huber's theory. And our goal in this class is to explain, well, the basic definitions in R theory and their relations to more classical theories of analytic geometry. But I just want to point out very briefly that there's also a whole different avenue you can go for localizing this, which even more radically, I guess, departs from Huber's formalism. So we already saw a small departure in that we were allowed to do slightly more localizations of a Huber ring than before because of this difference between valuations that are less than 1 on topologically nilpotent elements and ones which are valuations which are continuous in Huber's sense, but kind of even more drastic things are possible. So, in fact, so if, let's say C subset spec R is any constructible subset, so that means an intersection of a quasi-compact open with the complement of a quasi-compact open. So it's some locally closed subset of spec R, which is sort of finitely presented.
And a finite union of those, you mean?
Finite union of those, yes. Yes. So the basic, let me say the basic objects which sort of form a basis for the constructible topology would be something like you take D of G intersect the complement of the common zero set of finitely many functions. Then you can define an idempotent algebra in D RZ solid, namely to this on the level of this basic object, D of the complement of the zero locus of G, and then intersect the zero locus of F1 to Fn. To this you can assign the thing you get when you take R and then you invert G, and then you derived complete along F1 up to Fn. Which this final object only depends on the constructible subset. And by the way, if R is an Noetherian, then this derived completion is just the usual completion. But I want to emphasize that I'm taking this derived completion. This is a discrete object, but I'm taking this derived completion in solid abelian groups, or in a derived category of solid abelian groups. So I'm, so to speak, putting the inverse limit topology on this derived inverse limit here.
No such things, then you say that you view your constructible subset as a union of locally closed. You also look at the intersection and so on.
Yes.
So for each of them, each finite intersection, you do this, and then you take the you take the limit of this type of thing.
And it won't be concentrated in they'll have some homological. So
is it the case that the intersection of two basic things, what you get is a tensor product?
Yes.
Okay, so it is okay.
Passing of a complement to complementary close, then the intersection of them is trivial, but in general the algebra.
Oh yes, that's right. Sorry. Right. So maybe I shouldn't actually say that you can assign an idempotent object to any constructible subset. Maybe I should just say that you can assign, is it okay or no? Well, let me just say that you can assign an idempotent object to any basic constructible subset.
So you want to take the kind of the derived inverse limit of the idempotent object associated to all basic thing inside a given thing, but then you have a problem to prove properties of this. I don't know if it follows that it is an algebra or that.
In constructible locally closed subsets, or maybe.
What?
Yeah, constructible locally closed is.
If it's constructible locally closed, and you somehow take R gamma of this, so it could have some homological degree depending on the number of alpha and zeros to cover.
Yes. Yeah, so that's better. Thank you, Peter. That's better. Yeah. So then the only derived behavior comes from kind of union of principal opens. Thanks. Yeah, that's what I should be saying. Okay. So now, why are these idempotent? So recall that recall from one of Peter's lecture that the solid tensor product.
Do you recall what idempotent means?
Idempotent means that, thanks. So let's say that this is A. Idempotent means that A tensor over R solid derived A is the same thing as A of derived complete RZ solid, is derived complete. So to check the idempotency, you're asking that implies that so you're asking whether a map between derived complete objects by this fact is an equivalence, and that you can check by reducing modulo modulo the regular or the sequence f1 through fn that you're looking at, and then it just becomes kind of an obvious fact about a ring tensor itself being itself ring tensor over itself being itself, or rather any localization of a ring tensor over that ring with the localization is itself. So
you solitary or derived with derived. So you did something like this before? Or?
Yes, in one of Peter's lectures, he proved, well, at least a special case, and claimed it worked in general, that if you take a solid tensor product of two derived complete things, exactly in a setting like this, so you have a ring and you have finitely many elements, or any number of elements, I suppose, then the derived solid tensor product of connective objects, so in homological degrees, will still be derived complete.
Why? Because we proved it? Or?
Yeah, we proved. Well, Peter gave an argument for the special case of like P, and then but the general case is quite similar. So he gave the heart of the argument of the general case. Yeah, you have to write. Yeah, you have to do some work. You have to do some analysis, but it's not. Yeah, it's something we've discussed in previous lectures. Okay, so now so now the claim that I would like to make is that if C1 up to Cn are locally closed, constructible, and if their union, say set theoretically, is all of spec R, then these guys cover. Let's say these. The corresponding A1, these idempotent algebras cover DRZ solid. In what sense? So in the sense that, so if you have M in derived category of RZ solid, such that M tensor AI equals 0 for all I, then M equals 0.
Small thing, but union of CI, right?
Yes, thank you. Thank you very much. Yeah. Yeah. So, and this implies that you get so DRZ solid is some limit over. So in the first term, you have product over I of AI modules in DRZ solid, and then you have product over IJ, yeah, less than J, it doesn't matter, modules over the tensor product, AI tensor IJ, and the same thing, and then so on. You'll have some finite check thing. What? Sorry. Cover? They love, yeah. I like that. they're giving it a big hug. That cover. Yeah. So if they love DRZ solid, okay. Anyway. And the basic idea of the proof is that it suffices to show that R is generated by AI modules for varying I. So for example, if I just take the example of spec R is df union z of f, then R 1 over f is okay because it comes from here, and then the difference between R and R 1 over f is so generated in a finite manner, finitary manner. But this is the union of like R mod f to the n with some shifts. this is actually the fiber, sorry, here. And this is actually an RF complete module. So it lives in ZF. So if you take all modules over RF inverse and all modules over RF complete, and then generate things in just by triangulated category nonsense, eventually you're going to hit R, and then tensoring with anything, you'll see that you hit anything. And then using that, you can check that you get this kind of covering situation. So now let me just say what this looks like in examples. So so all of these, yeah, so we have the sort of the category attached to each element in our cover. The category attached to the pairwise intersections is just modules over this tensor product, which will also be idempotent. So let's take so example, let's say R equals ZXY. So let's take C1 equals ZX plus or minus 1Y. So we've got the whole locus where X is non-zero. And then we can look at the locus where X is 0, but Y is also non-zero. And then we can look at the locus where both X and Y are 0. That's the power series. Oh, sorry, I should add X and then complete along X. So that's Z bracket Y plus or minus 1 power series X. So then what happens when you start taking intersections of these guys? The most interesting thing is what pops out when you take the intersection. So the algebra attached to C1 intersect C2 intersect C3. You can just calculate these things using this basic fact that solid tensor product of derived complete things is derived complete. So what do you get? So when you do C1 intersect C2, you're tensoring this with this. That's just inverting X. So then you get Z, Y plus or minus 1, Laurent series X. And then you should tensor that over Z, X, Y in Z solid with this third guy, X, Y. Now both X and Y are inverted. But if you imagine not inverting X, then you'd have a power series here. And you could use this derived X complete trick to see that you can move this power series onto the inside here. And you get that this is Z Laurent series Y. Power series X with X inverted, which is just Laurent series X. So you get this kind of object here, where you're iterating so you iterate. In general, when you intersect a lot of these things together, you iterate completing and inverting. And it matters in which order you do this. But it all comes from this sort of commutative situation nonetheless, in this way of setting it up here. And I want to make the point that so these things are like kind of like higher local fields that people have studied, and they tried to study them from the perspective of topological rings, topological fields, and they were just terrible problems. Matthew's not here right now, but he even wrote a paper explaining that everything is horrible. But if you put them in the condensed world, then they're just perfectly well-behaved objects that you can work with. It arises from this natural procedure, and it's idempotent even in the derived sense over this ring, and it's just it just functions quite well. So I invite you to try to draw pictures of these covers to get an understanding for what's going on with these kinds of constructions. But OK, I think I'll stop here. Yes?
So for a finite type Z algebra R,
Yeah.
you explain the derived R solidification of the countable product of Z, and R is just a countable product of R. Right?
Yes.
And I thought it also true for something like the ring of power series, ZW bracket G, that's true.
That's true.
Which is not finite type.
That's right, but it's also not discrete. So, yeah.
It's determined by discrete things, right?
Yeah, so you could also take a finitely generated ring and an arbitrary ideal and look at the completion, and then you get the same statement. So the compact projective generator is just the product of copies of the IHES completion of R.
I see. And at the same time, if ring is not finite type, you also said it's union of finite type algebra, blah, blah,
Yes.
blah, right? And
Yeah.
is it easy to see for this case, ZW bracket T, it's equality?
No, but Z double bracket, no, sorry, that was a statement about discrete rings. So in general, maybe if you have some ring that's complete with respect to a finitely generated ideal, you'll get the good answer if your ring modulo that ideal is finitely generated. Maybe this is a good way to if the ring modulo the ideal is finite type over Z, then you'll get the naive answer. I think, yeah, sounds reasonable at least. Yeah.
Then I'm a bit confused. Solidification, solid part is determined by underlying discrete.
Yes?
So the same formula doesn't work for ZW bracket T?
But so Z double bracket T is a discrete ring?
Yeah, as a discrete ring, yes.
You're looking at Z double bracket T as a discrete ring? Yeah. Well, then it's just, then it doesn't hold. No, it doesn't hold, no. Okay. But if you look at Z, what to say? If you look at Z double bracket T non-discrete modules in Z double bracket T discrete solid theory, that's the same thing as in ZT solid theory. So once you've decided to, once you're complete, then it's enough to solidify stuff modulo that ideally you're complete along. Yeah. So does that address your concern? Yeah. Okay.
So what did again? So you said if you use the discrete ring and take the associative condensed ring, and you consider solid relative to the elements of the ring. Yeah. Okay. Just each element of the ring, and then you.
So if you consider this condensed ring with the product topology, you could either solidify every element in the underlying discrete ring, or you could just solidify T, and it's the same. In fact, you don't even need to solidify T. Sorry. I mean, you don't need, actually, it's just the same as in Z solid theory. So if you look at a Z power series T module in Z solid, then it'll automatically be solid with respect to everything. So in fact, this follows because, I mean, we showed that the topologically nilpotent elements will always be solid. And then modulo topological nilpotent elements, all you have is Z, which.
Is there a paper on Peter's lecture? I mean, a paper of Peter about this?
About what?
Solid tensor product. I mean.
This here?
Yeah.
He talked about it in this class.
Yeah.
Are you wondering if it's written down somewhere?
Yeah.
Yes, it is. Guido Bosco wrote down at least a case of P, like P complete. And I think also, isn't it right, Peter? I don't remember the title of Guido's paper, but I think also Lucas Mann wrote. Yeah, no, Lucas Mann wrote the general case in his thesis.
And the Bosco is in the Bretlins archive?
I think so. I forget the title of the paper in which it's contained, but he has some appendix on p-adic functional analysis from the solid perspective. And, yeah. The title of the paper? I said in this here he has some appendix to one of his papers whose title I can't remember, and the appendix is called something like solid functional analysis or solid p-adic functional analysis, or something like this, which kind of writes down the argument that Peter went through. Well, it was before, but okay. Yeah. Yeah. Yes.
Sorry, quite. Maybe this was a computation done earlier in the course, I'm just forgetting, but like regarding the control of the X groups, like the vanishing of them, like, so we had the proposition earlier for finite type.
Yeah.
So if I just, like, for example, take like ZP.
ZP, the p-adic integers? Yeah.
Was there a computation on that?
Oh, so you're wondering about this homological dimension results for ZP? Yeah, so there you get, yeah, now I have to remember, I think, yeah, there you should get also, it should just only be X1s. Yeah. That's actually that's easier to show than in the case of solid Z, because ZP is compact. So you can directly see that all of the finitely presented objects, it's quasi-separated. And all those objects are quasi-separated, and they're just like, yeah, inverse limits of finite ZP modules. Countable inverse limits of finite ZP modules. And that makes the whole analysis much easier.
So to summarize, so for, let us say, if R is a field,
yes,
then the finitely presented are quasi-separated, and in fact they are all given quite simply by, you just have the either infinite or finite product of the K, so that's okay.
Yeah.
For R a Dedekind domain, except the fact that you can have the Picard group is maybe not trivial, but still it's a product of, you have a resolution, you have product of copies of R, and then the kernel is something like product of maybe, actually you can use the Arenberg-Swindle to get rid of this anyway, so you can, it's always this okay, so it is a resolution of length 2,
yes,
like before, because
yes,
we don't have to worry, okay? And so we get there, and then in dimension at least 2, you do the proof that you discussed.
Yes.
Okay, that's the...
Yeah, and then there's, if you wanted to move to non-discrete rings, then you'd have to do more analysis and so on, and yeah. Yep. Okay. Thanks, everyone.